I have to thank you, Wasim. Where are you? I'm telling you not to come to the mic, but I'm thanking you because this is a great order, actually, transitioning from this notion of epistemic trespassing and the kinds of ideas that we need to be engaging with and how to engage into the last section of today, which is Foundations of Cryptoeconomic Systems. And this is quite an ambitious and grounding call to action, I'd say, to kind of try to, no, it's really well done, but it is a big undertaking to frame, what is this multidisciplinary, multi-perspectival dynamic that we need to be involved in. And I'll just say one of the things I took away from what you guys wrote was it's not just about getting these common terms or standards or these are all important things, definitions, all the things we've been talking about up to this time. It might be that we need to evolve our thinking. I mean, we need to have multiple disciplines, but maybe we just need even better capacity to think in multi-perspectival ways. So I think it's a really exciting beginning, and I hope to hear more. Thank you, Michael.
Hello. So I wrote this paper, Foundations of Cryptoeconomic Systems, with Shermin Voshmgir, who's the director of the Cryptoeconomics Institute at the Vienna University of Economics and Business. And I want to start by sort of motivating this with some quote-unquote foundational questions. And I have this, beautiful Venn diagram with everything on it, which the point really here is that we need to be not just interdisciplinary, but sort of polyepistemological, meaning that literally one way of thinking about what we know is insufficient to totally understand these new things. And so I'm going to explore that a little bit with you in this talk. I'm not going to read all of these questions to you because you can read, and you can read the paper further, but the idea is that these are questions that we ask about organizations and institutions and people and social systems, irrespective of the technologies that we use to intermediate those communities. And so we don't necessarily have to think of them as inherently technical questions, but we can't necessarily separate the evolution in the technologies from the evolution in the social systems that are sort of, their nervous system becomes these technologies. So I'm going to zoom in a bit on my personal epistemological sort of history. I'm by default already an epistemological trespasser because I sort of bounced between research on aerospace materials into complex social systems, into robotics, and then sort of back into more OR and large-scale operational automation stuff. And then found myself in crypto being like, oh wow, cool, I get to do all the things. And that's really exciting because, well, I like doing all the things. And so in this particular talk, I'm going to hone in on this sort of triangle here, where we look at economics, complex systems, and systems engineering as sort of the points that I use to triangulate cryptoeconomic systems. And you'll notice I've placed some edges on here because it turns out the fields I've actually worked in are closer to the edges: computational social science, operations research, and much of my PhD work was in what we would consider cyber-physical systems, which is a bit like applied cybernetics. So there's like a hybrid where we're automating or roboticizing systems that are larger scale in nature. So I make a quick note on sort of the role of technology versus the sort of social systems, because we are really dealing with these socio-technical systems. And I like to kind of place this as the technologies provide us capability. They allow us to do things, and that our sort of social systems provide sort of purpose for using those capabilities. So while we've talked quite a bit about our technical capabilities and our capability of understanding our technical capabilities and sort of like everything about this sort of far right side, I'm really appreciative for this session that we've had, this philosophy group, because now we're talking about purpose a bit more. And I think that's really important because at the end of the day, we do want to kind of create a vector for our new community to collaborate, and I think that comes somewhat from purpose. It doesn't mean we all have to have the same one, but I'm trying to acknowledge the fact that the social system orients around some purpose, even if the technological system orients around some capability. And this particular diagram I like for explaining the sort of bridge from the lower level technical stuff up to these social networks that exist on top of that infrastructure. There we go. Cool. So I'm actually going to go into those corners first. So we're going to talk a little bit about economics. Turns out economics doesn't even have a single well-defined definition of itself. So I've liked this paper, which actually is a prospectus on definitions of economics, which are mostly, hey, people define it differently. I don't need to go into all of the details, but it affects things like coordination and choice and human behavior. And what I find is that, especially when we're talking about technical capabilities, we need to address economics at two levels. One is systems and one is agents. And sometimes we get very agent focused, sometimes we get very systems focused, but it's actually important to remember that there are non-trivial feedback loops between systems and agents, that agents being part of systems actually cause the systems to change, and the changes in the systems actually induce a sort of different world for the agents. And when those systems have closed loops, we end up with these sort of emergent properties. And I particularly like this concept of micro, meso, macro. Actually, one of the authors of the paper I'm referencing is Jason Potts, who's one of our earlier speakers. And we've sort of unpacked this a little bit in the context of crypto, but it's really not specific to crypto. We're really talking here about what it means to look at the way that we relate our observations about individual behavior to our observations about system behavior, with the understanding that we're really only inducing a change on the incentives or the rules or the patterns available to the agents, and then they essentially express themselves through the patterns we give them, and that results in emergent behavior. So the level of control that we really have is often a lot less than we imagine ourselves having, and that we want to basically combine our ability to make observations about system properties we really care about with our ability to sort of induce some sort of structure or pattern on the set of things that an agent can do and what will happen if they do those things. So the second bullet point was complex systems or complexity science. So this is already a sort of trespassy field. It's one where we take really abstract mathematical concepts and transpose them across fields. And so early work in robotics that I did involved mimicking flocking patterns to get robots to actually flock. And so we literally went into the biology literature and looked at the way people explained this flocking behavior, turned it into mathematical algorithms, and told robots to do it until they started to do the thing we wanted them to do. And this is, for me, the essence of what complexity science is. It's not really caring what the medium is. It's about the processes, the systems, the way that parts compose into wholes, and the wholes exhibit properties that are not immediately inferable from the parts. And what's really interesting about this is that social systems are complex by nature, economic systems are social systems, and thus even as we sort of embed these social systems with new technological, as I said, nervous systems, we are still actually dealing with inherently complex systems. We do get a lot of benefits from cross-mapping our observations in nature or in other places where emergence or complexity is the sort of defining order. I won't go into too much detail here. We have a great session. People understand that there are multiple layers of these cryptoeconomic networks. I tend to make a point to describe this because it does tie in with complexity. We have sort of a networked structure with entities, we have sort of addresses and accounts and blockchains, and we have nodes. And these are in actually network of networks by definition, and they're not entirely observable. So while we can observe behavior in certain layers as a result of sort of the cryptographic tools, the system is, again, embedded in a social system where decisions are being made both at the sort of use of the technology or at the provisioning of it. So the nodes themselves, we can't always tell, for example, if the providers of the service are colluding. Sort of coming to my third sort of point on the edge, it's systems engineering. And here I'm really talking about engineering, the profession, the practice. So not necessarily the making of things, but the whole life cycle of making things, and in fact, making things for other people to consume. And so when you study engineering, you get courses in ethics, as we discussed earlier, and you get these sort of principled, applied approaches that say that your first duty is to the public that's consuming the thing that you're making, rather than even, say, your employer or whoever funded the project, et cetera. And I personally think this is an important ethical guideline because what we're building is, ideally, it's a social infrastructure of some kind, and infrastructure by its nature should be sort of safe for the public to use, and that burden tends to fall on the engineer, but not necessarily on one person, but on a community of practice that is responsible for producing the thing that they want to be infrastructure for others. And I could go into more detail, but this is a breakdown of a process for sort of designing and testing a design and sort of implementing and testing the implementation. And it's things that we see emerging in our community, but I think it's actually intrinsic to the practice of engineering. So another thing that fits into the philosophical component of engineering is models. And we talked a little bit about models at the end of the last talk. This is very important because sort of we are constantly representing things, both in the practice of designing them, but even in the things we create, we embed models of things. So it becomes the case that we end up having models of systems whose actual instance includes embedding of a model. So there's a kind of recursive turtles all the way down thing going on that if you don't quite take the time to unpack the sort of epistemology of models, you can sometimes get run aground. And for me, the main focus here is just acknowledging that because we're doing this, we're making subjective choices. Whenever we decide to model a system in a certain way, we have essentially imposed on that system that representation or that understanding. And so to kind of tie it into the tail end of the questions on the last talk, there was a proposed model of what a Satoshi might be. And if you took that model, then maybe you could argue that it was unique. But it was actually presupposing that you accepted that model. So we could make something inherently performative by deciding that we agreed with that, and then embedding that representation in things that we do forward. Then that thing is no longer just a supposition. It becomes part of the new version of the system. And I think especially in cases where we're literally building things out of mathematical and computational models, we need to be aware of the fact that our models, as we construct them, are actually part of the things that we make. And so that brings me to computational social science, which is where we actually start doing this and asking questions about what might happen. In this slide, I'm really just highlighting one thing, which is that there's this overlap between the sort of system, the thing that we've modeled in a maybe deterministic or objective way, or at least we've made our claim that it works this way, from the part of the system that's inherently social, and that we're modeling an agent as expressing something. If they're solving an optimization problem, then they're still expressing that optimization is what they want to solve. And a lot of the times our social systems models make really strong assumptions about agents, and that it's very important to remember that we actually want to play test that, maybe with people, maybe getting data from behavioral economics, maybe actually playing games in real life where people mimic the roles of the agents, and try to understand that the agent in the computational social science model is expressing something. So there's actually a limitation to how much we can do just by modeling data we have from the past, or by just sort of supposing as an optimization going on, which isn't to say we shouldn't use the tool. It's just important to remember that computational social science is still social science. And so we're using computational and technical tools to investigate social questions. Okay, so last one of the sides, operations research. So I'm going to make a pitch for people who are interested in this community to pay a lot more attention to the OR literature, and that's because OR has been solving messy, dynamic optimization problems under highly heterogeneous goals for ever, decades. Because although the methods are imperfect and messy, they have this sort of property that they sort of emerged from the real world, and people are like, yeah, well, I can't solve an interlinear program in fast enough to use it in this, but I'm gonna approximate it this way, and it's more or less gonna work, and I didn't go out of business, so I'm gonna keep doing that kind of thing. And it moves a little bit away from the toy models that we tend to construct in the computer science or mathematics literature, which they feel great. Like, you write a proof that, oh yeah, this is the best thing I can do, and then you don't see anyone do it ever. It's because that model that you created isn't actually a good representation of the real decision facing the party in the real world. And so there's some I think, a lot of value to come from both trespassing to and inviting people to trespass from the operations research literature. And I call out the two organizations here, Informs and SIAM, which SIAM is the Society for Industrial and Applied Mathematics, and Informs is, it's basically operations research and management science. In my particular research, I've been focusing on applying methods that are sort of dynamic and dynamic in nature, and that involves sort of this simulation modeling, mixture of data science and sort of, well, OR techniques. And we built the software called CAD-CAD. It's a Python package. It kind of connects right in with NumPy, SciPy, and other tools. And we go through a kind of workflow that allows us to sort of look backward at observations in the past and use data to fit stochastic processes or machine learning models, to combine that with various models from, say, behavioral economics, et cetera, and to sort of project in the future what might be a consequence and sort of iterate in loop. And this looks a lot like a workflow that would appear in a standard OR problem. Might depend on the size of the company, the strengths of the team, but it's sort of sound in its sort of continuous data-driven decision-making process, and you can use it for both design and for governance, because you can sort of fit models you have and make estimates kind of about where you're going and steer based on those estimates. And sort of the practical automation of this in the context of large-scale physical infrastructures is cyber-physical systems, and I consider this to be sort of systems engineering cross complexity science. And I won't go into too much detail here. This diagram is from the Tolmay project at Berkeley, and as you can see, the definition of a cyber-physical system is remarkably similar to what we think of as a crypto network. In fact, I'm going to pause for a moment to let you read that, because I came across crypto systems, and that was the first thing that I thought, like, oh, it's a cyber-physical system, right? But that's not common in this community, so it kind of brings back that need for epistemological trespassing. So I'm going to sort of give you guys a sense of where this has all taken me. I use robotics methodologies, and they have to do with this concept called a configuration space. And that's kind of weird, because it's like a topological space, like a mathematical thing that represents the sets of states that a system can be in. But it turns out, as a designer and analyzer of cryptoeconomic systems, this is what's really at our disposal, because we can control the set of states in the on-chain system, and we can control the domain of actions, or the admissible things, the things that we will let people do and what will happen when they do it. But we actually can't make them do anything, which means they can explore the whole space of configurations we've allowed them. And I use this robotic arm example, because if I put a robotic arm on the table and I give you a controller that allows you to move it, you won't be able to move it outside of the set of configurations the robotic arm allows. And you might actually manage to do something with it if you're doing it that alone, but if I hook up 3 more controllers and give them to your friends and say, cool, try to do something, you're going to have a coordination problem, or you're going to disagree, and you're all going to do different stuff, and the arm's going to flail around, and it's going to be weird. But what's cool is it didn't leave the configuration space. Nothing you can possibly do with those controllers is going to change whether or not the arm stays in its configuration space. And although this is sort of a mathematical sort of differential topology thing, it's really strong. And any properties that are inferable from the configuration space actually hold. So I'm going to do a rapid fire click through of what this looks like in crypto, because I don't have a ton of time left, but hopefully it'll motivate you reading some of my forthcoming work. We actually describe bonding curves in terms of configuration spaces in the way that's closer to what you would see in robotics. So we have system-level states and agent-level states. We put them together. We look at the way the rules tell us that the agents can change the system, but we actually here define the invariants, the things that are true for every point in the configuration space, and that allows us to do things like look at the curve itself and see how the agents can move it. This is system level. It shows you the bonding curve as you often see it when people talk about things like the Bancor equation. You can see it from the agent's view, which is actually a more traditional sort of economic-like curve where you have a sort of trade-off, and an agent can exchange one thing for another and find a point on this space. So it's their view or their slice of that configuration space. And then as a robotics background person, you could describe these things using block diagrams. We think of them as trying to, in the case of a bonding curve, estimate some hidden belief of the price, which turns out doesn't exist because everyone has their own thing that they might be expressing. So the price is at best an estimate of the collective sort of an error from the collective preference or belief of the price. So we can start to dig at that and try to understand, well, we can observe some things and not others. How can we mathematically make arguments about the things we can't observe using only the things we can observe and what we know about the very shape of the space because we designed it with our configuration space. So here's a quick plot. It kind of shows you that, oh, wow, these things actually kind of can be thought of as estimators. They have a non-trivial estimation error, but if you look at a sequence of actions and think of them as expressing price preferences, then the sort of spot price of a bonding curve gives you something that like genuinely looks like an estimator. Maybe a noisy one, but an estimator nonetheless. And I will close out, I think, by showing you what happened when we threw some data into a model of Uniswap from the real history. And so that this is a little interesting because it's actually a more than 2D configuration space because it doesn't just have swaps. You can add liquidity and remove liquidity, but the actual constant product market maker, as people call it, is having a changing constant product through that liquidity adding and removing. So the area of the square is your so-called constant product, and the curve that you can see is the invariant that would be preserved if you weren't changing the liquidity. And we basically just grabbed the data from the F-die pair and ran it through a mathematical model that was a representation of one of these configuration spaces, just to kind of show that it's not just math, scribbles, and notes. You can actually combine data with these kinds of models and get a sort of deeper understanding of what these systems look like. So I will end on that. So I'm saying our economy is a evolving cyberspace, and we are changing the shape of it. And we need to actually be conscious of the fact that we're doing that and actually think about the ethics of engineering in our effort to, like, build a new economic infrastructure.
Are you up for some questions? You up for some questions? Sure. Hell yes. Good. Well, we have coffee awaiting us after this, but let's give some thought. And yes, come up to the mic.
Michael, yes, I had a question. Can you expound more on how you see models embedded? Because the system is the model and the model is the system.
Sure. So I think what I'm going to kind of take a very the concretest I can do is to talk about this in terms of automation and control. So if I build an HVAC system and I have in it the ability to heat and cool my house, and I don't actually put a thermostat in there, I just have heating and cooling. First, I would have to use myself and sense whether I'm hot or cold and actuate directly and change the temperature. But if I add a thermostat, I'm not adding a thing, I'm actually adding a model. I take a mathematical representation of the system, my house, and give it a set point, something I want. And so I've changed the input from me actuating to me telling the thermostat the temperature I want it to have. But now the heating system is no longer the system it was before. It's the system plus a model. And if we wanted to model the house, the closed-loop system with the thermostat, we need another model, one that accounts for the thermostat itself, which is an inherently mathematical object.
Phenomenal. Go ahead.
A very interesting perspective. I just have, I guess, two comments / questions. And one is, there might be a reason, I guess they're both connected. So there might be a reason why not only crypto, but I guess economics in general hasn't embraced OR and as part of the discipline. And it might be just the interpretability of many of these tools and results. So what can you talk about that, and what can crypto do differently? And the other question is more about these sort of embracing complexity approaches sometimes miss out on the unknown unknowns, those things that we cannot even model even probabilistically. So I guess, what can you comment on?
Yeah, let's break that up a little bit at a time. So I'll come back to the unknown unknowns. Let's start with OR. So I think the reason why we could say that OR isn't embraced in economics is not actually because it's not embraced, it's that we've categorically separated them. A lot of OR has got its origins in economics, and they solve problems at different scales. And there's this inherent locality to the solution of an OR problem in context. It is a specific instance of a decision problem in practice, but you would argue that every time you do a portfolio optimization, you're actually doing something that is in the class of OR problems, not necessarily in the class of economics problems, but that's the artificial distinction. So it's a bit about the way the two fields relate to each other and their history, and the invitation to pay more attention to the field is less that it should subsume economics, but that they're actually a lot more related than I think the fields often give themselves credit for. In terms of complexity and sort of unknown unknowns, I think the reason why I started with this comment about being polyepistemological is that I think the idea is that what you can reason about or know or even believe that you know depends on some assumptions that you make, and that actually I think the complexity science field does a pretty good job of starting with the premise that there are as yet unobserved things that will later change your interpretation. But I think that's a fundamental blind spot that, it's almost a philosophical question where you say, given what I'm doing now, how much do I think or expect or want to take into account the things that I might observe in the future? And that actually comes back to modeling in a lot of ways, because you can build models. I think one that's commonly discussed is the sort of these probability distributions with fat tails that aren't integrable. And so they create this mathematical property where you no longer have an analytic mean, but actually by acknowledging that you might be in such a case, you already improve your ability to reason and make decisions. And ultimately, how we handle what we have yet to observe is one of those subjective modeling assumptions that we always have to make whenever we entertain sort of a scientific or engineering endeavor.
Great, go ahead, Wasim.
Okay, this is a fairly short question. So I did try to read your bonding curves and state configurations spaces paper. It was a bit too mathematical for me. So perhaps you can break it down for me. So bonding curve is kind of, I guess it's like a two-dimensional relationship between like the amount of supply of a token outstanding and the price per unit or something like that. It's at its simplest. So I'm curious about the model that the formal model that you've put together. Is it possible to extend that for additional dimensions? And how difficult will it be in terms of computational complexity to actually implement and enact that?
Interestingly, so maybe I'll work backwards. In terms of implementation, the implementation of things that are described using a configuration space isn't dependent necessarily on the dimensionality of the space. It's actually it's dependent on what the actual mechanisms are. So in these cases, we're describing things where there's a domain of an action. You take the action, and it determines the next state. And so all the actual implementation complexity, so setting the model aside, has to do with what I can do and how hard it is to compute where I am afterwards. And so that could range widely, even for low-dimensional systems, if you make really computationally complex like mechanisms. In terms of the bonding curve more broadly, I'm trying to keep it simple. I'll say that what we're basically saying is that you have a 2D phase space between a reserve and a supply, and that if you impose on that a one-dimensional invariant that is always holding, it's like a conservation equation, you get a one-dimensional system. But actually, there's another dimension that's super important to people, which is that sort of swapping action. So the swapping action implies another dimension, which is the price. And so the price gives you a third dimension, but it's still formally related because it's the limit of the actions. And so you can actually, if you look at it carefully, derive that that limit is like the tangent to the surface that's defined by the curve invariant that you imposed. So now you're in a 3D space, the reserve, the supply, and price, with two restrictions, so it's still only a line that you can move along, but it's explained or it's represented in terms of a differential sort of topological relationship, because it's not just the phase space, it's also your ability to move in it. But that's the system level view. The reason I have a couple diagrams in here, and I invite you to check out the paper and ask me questions, is that there's a sort of different perspective of the same the same mechanism from an agent's perspective, because there's a difference between how the system state changes and how the agent state changes, and those are coupled. And so we have this ability to reason about the relationship between the shape of the space, the bonding curve, and the set of actions available to the agent. And by not presupposing what they would express through using the mechanism, we actually can ask a different question, not whether they're rational, but what are they telling us by acting? And that's what brings us to the estimator's framing.
Phenomenal. Are there any burning questions that must be asked in a public space? Going once. All right, wonderful. So we are going to give everyone a break for some coffee and connection. I think I will just end with another quote, but from someone in our space. I don't know how many of you know Amber Baldet, but she said something that just never leaves me. She said, you know, the internet pioneers didn't foresee the corporate aggregation of power over the internet, necessarily. And so what are we doing here today to prevent the overlords of tomorrow? And I think all of this depth of questioning and figuring out of models and crossing disciplines and being uncomfortable and asking difficult questions and finding people to help fill in the holes is a part of what we'll do to prevent the next stage of maybe power takeover that we can't even quite understand where it will come from. So thank you so much. Enjoy connecting one-on-one. And we'll see you in 20 minutes back here.